speaker, Bertrand Toem. He is directeur de recherche at the CNRS and at Montpellier too. So, and his title is on the book.
Thank you. So first I would like to thank the ICM organizers for allowing me to give this talk. It's a great honor to be here. And let me start by mentioning some collaborators related to the mathematics of this talk. So there is Tony Pantev, Michel Vaquier, and Gabriel Vezzosi, and also more recently Daniel Kalak, and some aspects with Ludwig Katzarkov. And the aim of this project is the study of modularized spaces of sheaves on compact-oriented manifolds from the point of view of homotopy theory and deformation quantization. So, in order to explain a little bit more this aim, let me immediately give you the main theorem. It's a simplified version in the sense that it follows from a more general theorem, but it's general enough, I think. So I start with a complex reductive group with the algebra little g. Suppose that I have a fixed G invariant scalar product on G. And X will be a compact-oriented manifold of dimension D. And here I'm using manifold in a rather general sense. So it can mean a compact-oriented topological manifold. And oriented means oriented in the topological setting. Or it can be a smooth projective complex manifold with an orientation in the sense of holomorphic orientation. So a fixed isomorphism between the canonical sheaf and the trivial sheaf. And the theorem states that the modularized space of G bundles on X, bun G of X, suitably considered as derived algebraic stack, possesses a canonical n quantization, and this n depends on the dimension. So the purpose of the talk is to explain and comment this result. Particularly, I want to emphasize these two red things here. So I will give you some ideas about what I mean during the talk. Okay, so that's the plan of the lecture. I'm going to start by general things about deformation quantization, just to explain what I mean about this. I will explain what the theorem says in low dimensions, and how it is related to well-known objects or identified objects. Then I will switch to derived algebraic geometry and will give a little bit of definition of what derived algebraic stacks are and why they are useful. And then I will finish by a sketch of the proof of the existence of this quantization. It's not really a sketch, really, just some ideas. Okay. So, what's a deformation quantization? Well, I put principle, but it's almost a definition, I think. I start with a commutative object, and the deformation quantization is a formal deformation of X into a less commutative object, X H bar. So here, what is maybe a little bit not classical is this less commutative.
No, object is not object. What is object?
You will see in a minute. Okay? It can be a ring, it will be a category later on. Okay, that's a general, non-definition. So H bar is a formal parameter here. And X H bar is a formal family, and it recovers X when H bar equals 0, and X bar when H bar is different from 0, well, whatever it means, it's less commutative. We will see also what it means later. So two fundamental examples are the following. So this will answer your question of what object means. So if X is a manifold, the object is not going to be X, but OX, its string of functions, considered as a commutative ring, and then the quantization of X is a formal deformation of OX into an associative algebra. That's typically what's happening in the classical setting of quantization of symplectic or Poisson manifolds. Another example, if I take G a group, it will be an algebraic group most of the time, and its category of representations. Then it's a tensor category, and the quantization of G is going to be a formal deformation of G as a monoidal category. And this monoidal structure can be symmetric, graded, or just associative. We will see this a little bit later also. So objects, in the first case, objects are just rings. In the second case, objects are monoidal categories. Okay, and that's what's happening in quantum groups. So in this lecture, the deformation quantization will be realized as formal deformations of categories. That's the point of view I'm going to take. And possibly with monoidal structures. So they won't be just categories, but they will come equipped with monoidal structures. And I don't know if ubiquitous is actually correct, but it's because categories, you can find categories everywhere. So if you have a ring, you can look at its category of modules, and you can see the ring through its category of modules. If you have an algebraic variety or scheme or stack, you have a category of quasi-coherent sheaves. If you have a group, you have this category of representation. So categories are very useful because they just, starting from objects of very different nature gives you categories. And it's a way to talk about all of these objects in a unified way. And in these three examples, they are all symmetric monoidal categories. So if A is commutative, I didn't put commutative here. And what I meant at the beginning by commutative object really means that this monoidal structure is symmetric. So the symmetry here is related to commutative. And less commutative, which will mean less symmetric. So typically braided, associative, and we will see some other notion will be less symmetric than just what symmetric monoidal means. Okay, so this is what we're going to do. We're going to take symmetric monoidal categories and deform them into less symmetric monoidal categories. Okay, so let me now highlight the theorem with some well-known objects. So in dimension 2, here is a relation with low-dimensional topology. So suppose X is a compact-oriented topological surface, and G bundles, as you will see, in this case, will be a representation of the fundamental group with coefficient G. So the moduli space of G bundles can be realized as an algebraic variety. Just I take the affine variety of maps from pi 1 to G and mod out by G, by the conjugation action. So this is an affine algebraic variety. It has a ring of functions A, and it has been introduced a long time ago. There is a non-commutative, natural non-commutative deformation of A as an associative algebra called the sky algebra. And as far as I know, this has been introduced by Kaufman. And this non-commutative deformation is really this zero quantization given by the theorem. Here, L is 0 because the dimension of X is 2. Okay. So in this case, when X is a compact-oriented topological surface, the theorem gives essentially, well, I said part of because it's a little bit more general, but essentially it gives this kind of algebra. So now let's see the case of dimension 0. So X is a point. So principal G bundles are just, they're all triple, but they have many automorphisms, and it's a bad idea to neglect them. So the moduli space of G bundles on a point is not really a point itself, but it's a point with an action of G. And most of the time this is denoted by BG. So it's like an orbifold point, if you want. And, well, the technical term is that it's an algebraic stack, which is an algebraic version of orbifold group point. We will come back a little bit later to this. And it can be alkylated by its category of quasi-coherent sheaves. And quasi-coherent sheaves on BG are actually exactly representations of G. So it's a tensor category. And the quantum group is one way to see quantum group is to consider them as non-commutative deformations of the group G. And one incarnation is a formal deformation of hub G as a braided monoidal category. And this braided monoidal category, which is the deformation of hub G, is the 2 quantization given by the theorem, where here n is 2 because the dimension of X is 0. So remember that this n here is 2 minus the dimension. So in dimension 0, we find back essentially quantum groups. And the theorem is just states the existence of quantum groups. So let's see a little bit of dimension 3 in relation to Donaldson-Thomas theory. I'm going to be a bit fast here because I will come back to this on the last, or one of the last slides. So suppose that I have X, a smooth projective threefold, and oriented means it's scalar DRO, so and it comes with a fixed isomorphism, fixed realization of the canonical. So now principal G bundles on X are just principal G bundles, and they form a rather complicated moduli space. So here we reach a place where really derived algebraic geometry is needed. But let's suppose that there is a moduli space which is complicated. It's not quite an algebraic variety, but just assume that there is like an algebraic variety as a moduli space. And that's going to be enough for the explanation. So it's very singular in general, but it has a nice local structure. It's always given locally by the critical locus of a function. And it's actually true Zariski locally, that's a theorem of choice and collaborators. And these local functions give some algebraic differential equations. I hope I got it right this time. F prime being F prime F. And if I look at the sheaf of solutions to this, that's exponential F, it gives me something like a perverse sheaf on this moduli space here. And the Euler characteristic of this perverse sheaf may be restricted to a nice part of the moduli space where we fix numerical invariants, are by definition, or more or less by definition, the Donaldson-Thomas invariants of X. And this sheaf E here, it's not quite what the theorem gives, but it's very, very much related to what the theorem gives as a -1 quantization. And again, I will come back to this at the end of the talk. The precise relations are still unclear at the moment, but I can explain why they are closely related. So in dimension 3, this theorem is something very much related to Donaldson-Thomas theory. And in higher dimension, as far as I know, this quantization of G of X is not identified yet, or at least I don't know how to identify it with something that already exists. Okay, so I start to give you maybe some more details about the object involved in the theorem, and maybe a little bit of definitions. And I will start by saying a few words about the derived algebraic stacks and how they are useful and how they are necessary for the theorem to hold. So the first observation is that algebraic varieties or schemes are not enough to consider all aspects of moduli problems. I mean, this is already known because we all know now that algebraic stacks are needed when objects have automorphisms in order to have nice moduli spaces. But more is true, algebraic stacks are also not enough. And one reason is that even if you construct them as algebraic stacks, they are often very pathological. And derived algebraic stacks, it's an extension of the notion of algebraic stacks. It provides a setting in which moduli problems have better solutions, and just because they become less singular, they don't really become smooth, but they are less singular. And they are more easy to describe. And we will see examples in a moment of how these two things work. There is a price to pay. The price to pay is, does it work? Ah, okay. Is that there is a heavy technology of higher category theory or homotopical algebra in order to work with these objects here. I'm going to give very simple definitions and hiding all the technical aspects. The theory is quite technical and it really needs this higher category theory. And ultimately, you really need infinity categories in order to make sense of many of the constructions. So that's the price to pay, but you can just think of this as some kind of black box and just use it in order to do derived algebraic geometry. Okay, so let me start with derived schemes and the definition. So a derived scheme, that's everything is over C here, with a more general definition without the base. It's a pair, XAX, that consists of a space X and a sheaf of commutative DG algebras AX. So the main difference here from the difference with the definition of a scheme is this DG here. Okay? If I define a scheme, I have a space and a sheaf of ring. Here I have a space and a sheaf of commutative DG rings. And there are two conditions. First, if I take H0 of this DG ring, I get a sheaf of rings. and the condition is that this real space is a scheme. So if I forget anything which is not in cohomological degree 0, I do get a scheme. And the second condition is that these higher cohomology shifts are quasi-coherent over this H0, which makes sense because H0 is a scheme, and also they vanish for I positive. So here I'm using the cohomological grading, so the differential increases the degrees. That's the definition. It's a pretty simple definition of what a derived scheme is. I'm not going to tell you what are morphisms between derived schemes. This is where it starts becoming complicated. So, but as an object, it has a simple object. But they live in rather complicated categories. Okay, a few examples. I find derived schemes. If I start with a commutative DG algebra, so it has to be non-positively graded, this is this vanishing of Hi. I can define a derived scheme spec A, which is just the spectrum of H0. So H0 is a ring, I just take it, the usual corresponding algebraic variety or scheme. And there is a sheaf of DGAs given by the families of localizations. So if I have a DG algebra and an element, I can localize the DG algebra over this element. Well, you do have to work a little bit to make this meaningful. Okay, and a derived scheme locally is always of this type. Okay. Now here is another example, a self-intersection of a smooth variety. I'm giving you the local models, and globally everything behaves locally like this. So if I have a closed dimension of smooth affine varieties, I can look at the fiber product, but I don't compute this in schemes, I compute this in this complicated category of derived schemes I didn't define. But as I said, there is a nice category of derived schemes, and this is the fiber product inside this category of derived schemes. Then I found the spectrum of a DG algebra, which is essentially the free commutative DG algebra over the column under integrament. And maybe a third example is what I call Euler derived scheme. Start with a smooth variety, again, it can be non-affine, and you can just globalize the construction. And here, vector bundle with a section, there is a derived scheme of zeros of that section, called the Euler scheme, and it's given by the spectrum of the Kosul resolution, the Kosul complex associated to V and the section S. So S has no condition here in particular. If S is not transversal or not in generic position, this might have a lot of interesting cohomology, and these derived schemes might not be just a usual scheme. Okay. So now, derived schemes relate to schemes in the following way. If I have a derived scheme, I have the subscheme H0. Now, H0 of the structure sheaf is a quotient of the structure sheaf, so it's a subscheme. It's a closed subscheme. And locally, it looks like the natural projection from A to H0 of A. And the important fact is that X behaves as a formal thickening of H0. And it means that all the information encoded in this higher cohomology of the structure sheaf, you have to think of them as some kind of generalized nilpotent functions. And one reason this is true also, if you look at this inclusion by definition, it's an homeomorphism. They have the same space. Okay. So I really think that the derived scheme is like a formal thickening. It's a non-standard formal thickening, but it's a formal thickening of a scheme. And it behaves very similarly to the inclusion of the radius part of a scheme inside a scheme. So if Y is a scheme, I have the radius subscheme. This situation here is very close to this situation here. They really behave the same way. Okay, so I can go on and define derived algebraic stacks. I mean, if you know what are algebraic stacks, you will understand this definition. If you don't know, probably not. But I mean, just it gives you a way to, well, it's a little bit of definition, but it shows you that most of the things you can do in algebraic geometry can be generalized to derived algebraic geometry in a rather straightforward way. So a derived algebraic stack is a quotient of a derived scheme by an action of a smooth groupoid. So let me be a little bit more precise like this. So I start by defining a groupoid object. So derived schemes from a category, I can talk about a groupoid object, which is the data of two Derived schemes, x0 and x1, with two maps, and there is also an identity map I didn't write, with a composition, and this is the fibered product in Derived schemes, and a bunch of conditions I'm not writing. And the condition, I should have written down. These two maps are supposed to be smooth. This is related to the smooth cutoid. So the typical example, and that it already gives a very large class of interesting Derived algebraic stack. It's not an artificial example. If I start with an algebraic group, and I start with a commutative DG algebra that has an action of G, which means that A is a commutative DG algebra inside G, really. It's a DG algebra of representations. Then I can form the quotient stack, which is this spec A cross G, and this is the projection, this is the action map. And that's already an interesting class of Derived algebraic stack, as I said. You know, many examples are of this type, or maybe has stratifications for which the strata are of this type, and so on. So that's an interesting class of example. So you can see algebraically it's pretty simple. It's a group and a DG algebra with an action of G. But then it leaves again in a rather complicated category. So I don't say where this quotient is taken. That's where it starts to be also technical. But there is a nice category in which it is taken. So that's what I said. The algebraic stacks can have easy algebraic description, like just a group and a DG algebra with an action of this group. But they live in a very complicated infinity category. Okay, this is just what I said. Okay, so what's the important example for us? It's given by the following theorem, which is a theorem I proved with Gabriele Bezzozzi, and there is also an alternative proof by Lohi using a representability criterion. So if X be either a smooth and proper algebraic or a compact topological manifold, and Y is a Derived algebraic stack, which is locally defined type, okay, some technical condition, then there is a Derived algebraic stack of maps from X to Y. And it is characterized by the following universal property. So for any Derived scheme S, the home space from S to this map is just the home space from S cross X to Y. So it represents the functor of maps. So first, it's a non-trivial statement. I mean, it's not just something abstract. So it implies the existence of many Derived algebraic stacks representing moduli problems. So here are two examples. Derived trivial schemes or code schemes can be deduced from this. The Derived moduli of vector bundles also. And more complicated objects like Derived stacks of stereo maps or derived even higher stacks of objects in Derived categories and so on. So this is a very useful statement. I mean, it gives you a way to, once you have a Derived algebraic stack, you can construct new by just mapping into it from a nice object. And it gives you a way to construct new examples. It's quite useful. Check the time. Okay. So this theorem can be used to give a definition of Bun-G of X. That's the main object of the theorem. So if I have an algebraic group, and X is again either a smooth proper variety or a compact topological manifold, there is a Derived stack of G bundles on X, which is by definition mapped from X to BG. BG is this, I should have written down this before. That's the groupoid with a point and G acting trivially on the point. So it's just the point mod out by G. And it turns out that maps from X to BG are G bundles on X, so that's a meaningful definition. There is another way to define what is this guy, but that's the most easy way. And it's useful to think of it as a mapping object. What's interesting is that some part of this thing can be schemes, actually. It can be actually smooth varieties. Some open part or some nice part of this can be a smooth variety. But still, it's a map from something to a stack. So when you map a scheme to a stack, the corresponding moduli space can be a scheme. And it can remove all the stack thing. So it's interesting, I think. Okay, in the topological context, meaning when X is a topological manifold, that's quite easy to describe. I'm not sure it's very useful for the talk, but let me show you. So over the point is PG. Over the circle, it is G mod G by the conjugation action. Over the sphere, or the higher dimensional spheres, it is of the form spec A mod G, where A is a G equivariant to DGA, And this A here is explicit, just a symmetric algebra over the dual of the Lie algebra of G, shifted by d minus 1. And then, if you want the general formula for X, you do a cellular decomposition of X. Then this map will have a decomposition, this mapping space here will have a decomposition into iterated fiber products, and the elementary pieces will be these things. So it's a way, if you know a cellular decomposition of X, you can more or less compute this G of X, or at least have an idea of how it looks like. Okay, so I think this is just some general terminology, some general thing about Derived algebraic geometry. So by definition, Derived algebraic geometry is the study of Derived algebraic stacks. And I just wanted to say that there are foundations, I say modern foundations, in the sense that derived schemes and derived algebraic stacks used to be defined differently before, like DG schemes, things like this. But this really appears in these modern foundations. And it has been settled down in the last 15 years, so in the work with Bezzosi, and there is also the work of Fleury in France. So what does it bring new? Well, as I said already, derived algebraic stacks are better behaved than the underived analogs by many aspects. But I want to emphasize the aspects I'm going to be interested in this talk. And what is important for us is that they have much nicer infinitesimal behavior. So let me illustrate this by some infinitesimal aspects. Well, first it was called infinitesimal computation, but this is not really a computation. But let me show you why they behave in a nicer way than usual algebraic stack systems. So if I have a derived algebraic stack, well, it's an object that locally looks like a DGA, and DGA has a tangent complex, which is like derivations of these DGA, TG derivations. And I can globalize this thing to get a tangent complex, which is a quasi-coherent sheaf on Z, or an object in the Derived category of quasi-coherent sheaves on Z. I will tell you what this is, but I'm going to tell you in a moment. But I mean, it's what you can think. The Derived category of sheaves of modules over a sheaf of DGA. So that's the Derived derivations on G, the Derived tangent space, if you want. And now, the interesting thing is that when Z is a map from X to Y, when X and Y are like in the theorem, I was mentioning that this is a Derived algebraic stack. Then we have a nice formula for this tangent complex. It's given by a direct image of an inverse image of Ty for P and F being these two maps. So P is the projection from X cross the mapping space to the mapping space. And F is the evaluation map. If I have a point in X and a map from X to Y, I get a point in Y. So I can start with the tangent complex of Y, put it back here, and then integrate over X to get a sheaf here, a complexes of sheaves here. And that gives you back TZ. And this formula is completely wrong if you remove derived everywhere. You can have a Z, which is a mapping scheme between two schemes, say, and this formula is wrong. And it's even worse than this. There is no formula for the tangent complex of a mapping scheme in general, except in some very degenerate case. So that's one aspect. I mean, the tangent complexes are very easy to compute. So this is related to what I was saying, that they are more easy to describe than non-derived stacks. Okay, so let me continue with another interesting infinitesimal aspect of the Derived algebraic stack. Suppose I have Z and a point in Z, then little Lz will be by definition the tangent complex at Z, so the fiber at Z, and I shift it by -1. And it's a fact that this is a DG Lie algebra, or it has a structure of a DG Lie algebra, maybe an L infinity Lie algebra. And now, this DG Lie algebra, the nice thing is that it recovers completely the formal completion of Z at little z. And there is an explicit formula. Just this formal spectrum of a natural DGA, and this DGA is the completed Chevalier complex of Lz. So Lz is a DG Lie, I take its Chevalier complex. The formal spectrum of that is the formal stack, the formal completion of Z at Z. Well, this is true in the underived setting. But again, in order for this formula to be interesting, you need to know how to compute this thing, and you don't know how to compute this thing outside of the derived setting. So that's a justification why Derived algebraic geometry is very important in this talk. It's not really possible to avoid. And then there is a global version. Let me skip this, it's not necessary. Okay, so we're going to use this in order to define symplectic structures on Derived mapping stacks. Let me give a pointwise description first. Suppose I have a principal G bundle on X. So it's a point in map from X, it's a point in bund G of X. Then this tangent complex can be computed using the formula I gave you, and you find the cohomology of X with coefficient in the adjoint representation of E shifted by 1. So that's the sheaf, it's a sheaf of Lie algebra corresponding to this principal bundle E. You just replace the fibers which are G by their Lie algebras. It gives you a sheaf of Lie algebras. And you can take the cohomology of X with coefficient in this sheaf of Lie algebras, shifted by 1. So if I put the -1 here, I do get the formula for the Lie algebra I was talking about. And now what's interesting is that the cup product in cohomology, the cup cohomology of X, gives me a pairing on this tangent complex here. It has a degree, 2 minus d, so this has to be related to the n of the theorem. And it's not degenerate in cohomology, so it's not degenerate as a pairing in the sense of complexes. Okay, I can take two classes here, I can cup them, then I find something at E, tensor at E, use my scalar product on the Lie algebra to go to the cohomology of X with constant coefficient, and use the fact that X is oriented to get a number. Now, because of the dimension of the orientation, I do get this shift here. And one of the main statements here, which is useful for us, is that this pointwise description can be integrated into a symplectic structure. That's the following theorem. So bund G of X carries a canonical symplectic structure of degree n being 2 minus dimension of X. And if it has a canonical symplectic structure, it has a canonical Poisson structure by duality. And as a comment here, there is a hard part in this theorem. This pointwise description can be done globally, that's not difficult. What is hard is that to prove that this 2 form is Durham closed. And why is this so? It's because in the Derived setting, being Durham closed is not a property, it consists of extra data, and actually it consists of an infinite number of extra data. And so you have to construct these things. This extra data in the smooth case, for smooth variety, just disappear and it becomes a property. But in general, it's not. So that's why this theorem has a non-trivial content. Okay, so arrive at the last part of the talk. Just try to explain how this can be used. So I'm going to use this term here to deduce the theorem from the beginning, meaning that there is a canonical quantization of this bund G of X. Oh, and maybe a last comment here too. This derived algebraic stack, I can look at its truncation with H0. So there is a non-derived algebraic stack inside it, which is just killing all the derived structure. And now the form here restricts to a form on this truncation. It stays Durham closed, but it's highly degenerate, so it's not a symplectic form anymore. So this Poisson structure here does not restrict to a Poisson structure on the non-derived part. Okay, so just some, this is the missing thing in one of the slides. I didn't tell you what was a DQ of a derived algebraic stack. So here are a few lines to explain what this is. For Z being affine, this is just the derived category of A modules. Well, it has to be considered as a DG or infinity category to really make sense. I mean, for what I'm going to say to make sense. So keep in mind that this is not just a category. And up to quasi-isomorphism. And in general, if Z is a general derived algebraic stack, I just set the limit over all respect A mapping to Z. And this limit has to be understood in these DG or infinity categories. And each of these things has a modular structure because A is commutative, so there is a modular structure on the limit. Okay, so what's an n quantization of a derived algebraic stack Z? By definition, it's a formal deformation of its category of quasi-coherent sheaves. considered as an En monoidal DG category. So I have to explain what these are. And N can be negative here, so I have to give you some information about these two. So what's an En monoidal structure on an infinity category? It's an action of configuration spaces of points in Rn. So by definition, it's the data of infinity functors like this, plus some a lot of conditions, a lot of structures I'm not writing. So it means that you don't have any, so for k equal 2, for instance, it means you don't have a single tensor product. You have a whole space of tensor product parameterized by 2 points in Rn. So there is a 9-1 dimension sphere of monoidal functors. And then the higher coherences are given by the geometry of these configuration spaces. So you have to think of it as a continuous family of infinity functors from Ck to say parameterized by configuration spaces. So the higher n gets, and the higher commutative, or the closer to symmetric monoidal you are. So when n is infinite, E infinity monoidal really means symmetric monoidal. Because these configuration spaces are just classifying space for symmetric groups, and you do find a symmetric monoidal structure. But there is a hierarchy of commutativity constraint given by this En monoidal. So E1 is like associative, E2 is like graded, or maybe I'm saying this, yes, E2 is like graded, E infinity is symmetric, and there is E0 is like no monoidal structure at all, where there are some few discussions for this. And in general, because we are working with infinity categories, En is different from En plus 1. You know, as opposed to, if I was working with categories, it stops at 2. E3 monoidal would be symmetric already. Here there is no stabilization. And for n negative, it sounds like a trick, but there is an explanation behind. A deformation of an En monoidal structure makes sense as an E minus n monoidal structure, but the formal parameter has some degree now. So it sounds like a trick, but there is an explanation of why this is meaningful. So I'm not saying that there is a notion of En monoidal for n negative. I'm saying there is a notion of deformation of En monoidal for n negative. Okay, so what's the main statement about deformation theory of En monoidal categories? I have until 50, right? I have until 50.
Yes.
Right? Yeah. Very good.
10 minutes.
Okay, so now, by definition, an n quantization is a formal deformation of this thing as an En monoidal DG category. So you have to get a way to understand these deformations. And this is provided by this higher dimensional version of Koncevich's formality theorem. So that's the following theorem. I should have put some co-authors there. Okay. There's a dot. Kanak is also involved in some part of it. I mean, okay. Look, you can look at the notes in the proceedings. You have more precise attributions. So, so let's see the Derived algebraic stack. And now the deformation of quasi-coherent sheaves on Z as an En monoidal DG category are controlled by an explicit DG Lie algebra. That's the DG Lie algebra of polyvectors. So how does it look like? So I take the tangent complex of Z, I put it in degree n plus 1, so I shift it on the right in degree n plus 1. I take the symmetric algebra, it becomes something huge, and I take global sections. And then I shift back everything by n plus 1 so that Tz sits in degree 0. And the Lie structure is given by a version of the Schouten bracket. So I have a bracket on Tc and it extends to a bracket on polyvector fields. Okay, so when n equals 0, so when there is no monoidal structure, this is just usual, and say Z is a smooth variety, this is just polyvectors in the usual sense. And that's the usual DG algebra of polyvectors in Z. Okay, so this theorem is not a formal statement. It's called formality, but it's not a formal statement. This sentence is not from me. I can't remember who stated that. So let me tell you why. So when n equals 0 and Z is a smooth variety, this statement is Koncevich's famous formality theorem. Now, for n equals 1 and Z a smooth variety, it was conjectured by Kapustin in his ICM lecture in 2010. And for n strictly bigger than 0, and for affine maybe affine spaces or smooth affine varieties. Apparently it was conjectured by Kontsevich and Voronov, or at least Kontsevich told me this recently, but I cannot find a reference where there is an explicit conjecture like this. But it seems that there are some computations going in that direction in some paper of Voronov. So if you know, I'd be glad to hear where it is done. And one of the, so there are two proofs essentially right now of this theorem. So one is with Damien Galak, this is why I forgot his name. But a first step in the proof is to understand the deformation theory of EN monoidal digit categories without this, like abstractly. I give you an EN monoidal infinity category, I have to understand its deformation theory. And so we have to solve this problem too. And already for n equals 0, that was open. So you can see Jacob Louis' ICM lecture at the end, while the expanded version that is on his homepage. At the end, there is a deformation theory for categories and some open questions for that. So the theorem has a first step, which is a general understanding of deformation theory of EN monoidal structures. And then there is formality, which is the second part. Okay, I'm not going to say more about this. So how do you prove existence of quantization now? Well, it follows essentially from this N formality. So formality tells you that if you have a Poisson structure of degree n, well, if you look at what is this, a Poisson structure of degree n is essentially a Moivre-Cartan element in here. So almost by definition, it gives you a formal deformation. So if I have a Poisson structure of degree n, it gives you an n quantization of Bunge of x, or a formal deformation of dq-co of Bunge as an EN monoidal category. Is this all I wanted to say? Yeah, and we saw that Poisson structure exists because of this previous theorem that there are symplectic structures of Bunge of x. So this is how you prove the theorem. Okay, I have some few concluding remarks here in the last 4 minutes. First, if I fix a point in this moduli space, this quantization can be made a little bit explicit. Well, maybe I don't have the same standards as some people about what explicit means, but anyway, it's explicit for me at least. So let's consider Bunge of x, and I complete it at E. Then I know that that's the formal spectrum of a Chevalier complex, where LE is this DG Lie algebra, cohomology of x with coefficient D algebraic representation. And there is this non-degenerate product in cohomology. If you look at it carefully, you can make it a Poisson bracket of degree 1 minus n on this Chevalier complex. Well, I have to work a little bit to do it, but I can do it. And this Poisson bracket of degree 1 minus n can be quantized. So if n is 1, this is just of degree 0. If it is of degree 0, you use essentially a version of Kontsevich's deformation quantization. And if n minus 1 is strictly negative, then it's even more easy because you can use the fact that the higher Poisson operand is equivalent to the higher EN operand, and just choose such an equivalence. So there's a choice of an associator here, and look at this Poisson bracket as actually a EN monoidal structure on modules of these things. Maybe I got theory wrong. Anyway, so it's a bit explicit in the sense that it's really a perturbed version of Weil algebras, in the sense this Chevalier algebra together with this Poisson bracket or their quantizations. Because if you assume the Lie bracket to be 0 and n to be 0, this is actually Weil algebras. You just have a polynomial algebra, and then there is a symplectic form on the generators, and you just deform this commutative algebra into an associative algebra by the usual formulas. So this is really a version of generalization of Weil algebras at a given point. Then the content of the existence of quantization is that this local construction can be glued. Okay, so we have 1 minute to come back to dimension 3. So let's be back to dimension 3. I take Bunge of x. X is a Calabi-Yau, a three-dimensional variety. And then, by definition, my quantization here gives me a monoidal category, and now h bar has this funny degree, that it has degree -2. Right? Forget about this. The quantization is a monoidal category. Now, it is expected, and by expected means under some condition or maybe under some choices, you need one of these orientation data choice of this moduli space, which I'm not going to discuss. Maybe Kai Behind talked about this in his lecture. It's not expected to be true always. You need some extra choice maybe, or to prove that something exists here. You want to say that this monoidal category acts on a naturally defined category M. So M is a category, dq of z h bar is a monoidal category, and it acts on it as a monoidal category. And you can define well, if I remove h bar, if I have a module over dq of z, it means that M is a sheaf of categories on Z. It's like if you have a module over functions on a variety, it gives you a sheaf of modules. So you can describe M as a sheaf of categories, and locally it's given by, if you take potentials for which this moduli space is a critical locus, this is the category of matrix factorization. And the relation with the sheaf E is just that's the Hawking homology of this sheaf of categories M. Well, that's conjectural at the moment, but I think that's the explanation of how it recovers DT environments. Yeah, and I think I'm done.
Have any questions or discussion?
Can you comment on the relation to higher topological theory?
Could you ask the question more loudly?
If you could comment on the relation to higher topological theory.
Higher topological field theory. I'm not. Higher dimensional analog of? Of what? Sorry.
In the case of quantization, there is an interpretation in terms of topological field theory with the Katan-Evan.
Okay.
I'm asking you if there's a similar interpretation in terms of higher topological field theory.
I don't know. I don't even know the first thing you said, so I don't know. I mean, there is a. It's maybe related to what you said, maybe not. I don't know. There is an ultimate goal is to construct fully extended topological quantum field theory. So I don't know if this is related to what you said, but so I'm describing values over manifolds, but then you can work with boundaries and with Bordism and Bordisms within Bordisms, and they are organized into a nice infinity functor and blah blah blah. And this quantization is a quantization of this functor, something like this. I don't know if it is related to what you said. Sorry.
So you gave us some details about dimension 2, dimension 0, and dimension 3 cases. What about dimension 1?
I don't know. No, there is. It seems that there is an object you can construct. So you start with a group. You have the quantum group, and there is another category you can construct out of it. Which I'm not an expert. I'm sorry. It's like called Drinfeld-Yeatel modules, something like this. And this seems to be the output of the quantization. Does it make sense? So it's one of these funny double of the quantum group. So the quantum group acts on itself by conjugation and take the quotient.
Any other questions? It remains for me a little ritual to give you a present on behalf of the ICM.
Thank you so much. Thank you.